Thank you. Well, it's a great pleasure to welcome Professor Olaf Müller from the Humboldt-Universität in Berlin, who is going to speak to us. Well, he's going to give us a brief history of color metaphysics. So 30 minutes of a presentation and then 15 minutes for questions. Thank you very much, Olaf.
So thank you very much for the invitation to this fascinating conference. When I got the invitation from Joanna years ago, I was puzzled because there occurred to me to be some kind of misunderstanding. She asked me explicitly to speak about color metaphysics, probably not knowing that I had been resisting the tendency to do metaphysics all my academic life long. So I come from a tradition where you just don't do metaphysics because metaphysics is bad. So here is my pessimistic meditations about metaphysics in the subject of color. And the main problem I have, I did a lot of research about color during the last 15 years, and there's this principle, never trust a skinny cook. And I would translate this into philosophy of color. Never read a book about the philosophy of color which doesn't have color plates. And that excludes an enormous amount of the literature that somehow pretends to do something with colors, but they do it with their eyes closed. And that's a dangerous tendency in metaphysics where I want to try to resist. So what's metaphysics? The notion is pretty old. There's a book by Aristotle about metaphysics. He didn't name it himself like that. And a librarian who was puzzled where to put that book into the order of other books by Aristotle called it metaphysics, the book coming in the order now, after physics. That doesn't give us an answer what this crazy discipline in philosophy is all about. It's a super abstract discipline, and I'm one of those philosophers who is frightened of abstraction. We like the concrete. Now, the first questions in metaphysics that you will all know is, for example, what is there? For example, is there God? And if she exists, what kind of properties does she have? Or do we have an immortal soul? Or are we free? These are classical questions from metaphysics. But I believe colors cannot come into the picture here because they aren't as important as God, freedom, and our soul. So what could be another interpretation of what's meant by this issue, metaphysics of color, is maybe something ontological. So when we look very carefully at the furniture of the universe, what is there and what isn't there, then the question arises if colors belong to the furniture of the universe or not. Now, perhaps that's a bad question, and liking the concrete, I would translate the question into what difference would it make if there were colors as opposed to if there weren't colors? And maybe it makes a difference in painting. So, for example, if you degrade colors and push them out of the furniture of the universe, out of the things that really exist, then maybe you concentrate on drawing, and color isn't that important then in painting anymore. And indeed, the metaphysics which was opposed to colors led to theories of art where the people did not much invest in the knowledge of colors and in application of colors. So there you see that metaphysics can be quite a dangerous business. In my second meditation, I jumped to the Middle Ages, and there were two competing schools, the nominalists and the Platonists. And the nominalists say that there's nothing but individual objects out there in the world, for example, this very table or that very rose. And their opponents, the Platonists or the conceptual realists, claim that in addition, there are other entities than these concrete individual things. For example, the tablehood over and above all the tables. So we imagine that we have many tables there. And for example, you could say they all are not quite perfect. They try to be the perfect table, but they are not the perfect table. And the tablehood is what tells us what a perfect table would be like. Or about the color pink, we could say we have all these beautiful pink roses, and then in addition to the pink roses, there's the property of pink, a certain shade of color, you might want to say. Now, it's difficult to say what it means to claim that in addition to the concrete objects, we have these abstract things out there. And nominalists just say, as we don't need them, let's get away with them and let's speak only about concrete objects. Now, when you look at colors, one way of operationalizing this issue could be, you could think if you take all the pink things and you scrape from all these pink things the first layer, the pigments which color them pink, right? You could put all these pink pigments into a big basket and you could say, there's the color pink. But obviously, this is not what's meant by the idea of Platonism with respect to colors. When you want to claim that there is the color pink in addition over all the concrete pink objects, there's something more mysterious in this claim, and I confess I don't understand it. The third meditation is something which is still more dangerous about colors. So I go now to early modern ages when there was color research done in the sciences, as we saw in the first presentation today. And then there came up such an ideology that we have some qualities that are grounded in reality as reality really is, and then some other qualities are merely grounded in human perception. So they depend on the coincidences of our biological makeup. And some of these primary qualities, which were supposed to be the basis of what we do in physics, could have been the quantity of particles. So you imagine little particles and you can count them, and it's really objectively given how many particles are, let's say, composing a certain table or something like that. Then what's objectively out there, what's a primary quality, you could speak about the geometrical shape of the particles, maybe they are round, maybe they are cubes, or what have you. You could also speak about the objective arrangement of these particles in space. It's some geometrical quality which you might speak about. And you could also put them on a scalar and you measure their weight and you have the mass of these particles. So the physicists like to think that reality is made up of objects which have these objective qualities. They call them primary qualities. They are first out there. And then in the next move, they said, well, secondary qualities, that the bad stuff, that's what isn't really out there. That's what is made up by the human mind when you look into reality. And one of these things is the taste. So the particles themselves are supposed to have no taste. And when we have this beautiful cinnamon taste, it is made up by our mind and by our tongue. The interplay of the particle, the tongue, and the mind creates the taste, but the taste isn't out there in the world. Atoms don't taste like cinnamon, for example. And then the same is being said about colors. The colors aren't out there. What's out there is, we could nowadays say photons. You might say light rays of a certain wavelength. And they have these properties. The wavelength is a mathematical property. We measure it. It's, let's say, 600 nanometers. This appears green to us, but that is a human addition to what's out there in the world. In the photons themselves, there's no color. We could speak shorthand about the color of photons, but what it means is, in fact, a certain wavelength. And Newton, of course, was the master of mathematization, and his optics was the attempt to put mathematical numbers instead of the colors. He wanted to get rid of the colors, and in fact, when he improved telescopes, that was one of his main moves to get away with the disturbances of colors, and let's put them into numbers and let's have them secondary. There's more qualities that then are accused to be merely secondary, for example, beauty and goodness. All this is projected back onto the human being as though there was no objectivity about morals, no objectivity about aesthetics, no objectivity about colors and taste. This is a dehumanization of many human experiences, but it was a good principle for doing science. The question is if it's a good principle for doing philosophy or metaphysics. Now there's one danger in this. When you start wondering about it, for example, in the list of the primary qualities, where you have a lot of mathematics, mathematical properties are liked by this ideology, then of course the question arises, is mathematics something done by humans, or is it somehow objectively out there? And the objectivity of mathematics is a highly disputed issue in the metaphysics. Are there really the numbers out there on the Platonic sky, or what's that? For example, you might say the numbers are given to us by God and the rest the humans made in mathematics. So there's a lot of discussion. But as soon as you increase this tendency against secondary qualities, the danger is that also mathematical properties and everything might be swallowed up by the human mind. And the tendency leads us to an idealism, which could be interpreted as saying that perhaps all qualities and in the end all objects are merely grounded in human perception or in the way the human mind is organized. Perhaps there's nothing real out there. So you see, I believe, what the dangers are in metaphysics. And now, having seen all this abstraction, I would like to jump back to an idea that one might call naive realism. Goethe was one of the champions of that in the last century. Hilary Putnam, great philosopher from Harvard, went into different directions. The late Wittgenstein had some such ideas also. And there were opponents in this debate about colors now, Schopenhauer and Berlin and Kay. And the idea is here, naive realism is a realism with a human face, you might say. Things are the way they appear to us. Things really are that way. Of course, the rose is really pink. There are millions and millions of colors. And when we come back and say, well, all the things which we were talked out before are indeed existing, then the life gets nicer, the philosophy gets more colorful, and then you can, of course, start wondering which are these colors which are out there in the world. And physiologists keep telling us that we have the capability of distinguishing 2 or 3 million different colors. And then the ethnologists went out there into the different cultures and gave the people color plates. This was a set of colors they handed over to the natives, and then they asked basic color terms, and they should find out which is the best representation of, for example, what in the native language would be red, and so forth. And the issue was if this is culturally relative or if there's some stability in human perception, so that in different colors we might agree on what is the perfect example of red or the perfect example of yellow. And interestingly, these researchers found that there's a lot of stability across cultures, much more than one would have thought, relativistically speaking. And they came up in the end with 12 colors. Some cultures have only 3 or 4 or 5, but the first 3 or 4 or 5 are the same in all cultures. That was the claim. And when you look at the possibilities of really saturated colors, you get a beautiful amount of, for example, 60 different shades, which are all equally far away from one another. I see that the projector isn't that normal because the yellow comes out a little too dirty. And just when I spoke about that there could be perfect examples of some color tones, I wanted to remind you of the quarrels you have in your family and with friends about if this is now a really good green here or if it's not. And I would like to say, of course, there's a lot of individual aspects in the personal perception of colors. But when it comes, for example, to the color of yellow, we pretty much agree what is the perfect yellow and what's not. So I do it with my students from time to time. I make a competition. Everybody is supposed to bring the yellowest object to class. On a sunny day, we have to do it because otherwise one can't see enough. And then they bring tulips, and they bring books, and they bring other gadgets, knives, and so on and so on. And then I lead that discussion, and of course I have a lot of authority over my students, right? And I say, but could we agree that this object here is a little too orange, or a little too dirty, or a little too pale, and so on? With my authority, and of course I pretend to be nice to the students, with my authority guiding this discussion, we pretty quickly can agree that there's the one yellowest object and everybody agrees which it is. It's quite interesting that there's not much about taste here or individual variations. The perfect yellow, we agree easily. And by the way, interestingly, in the case of yellow, this game goes the easiest. When it comes to green, it's already much more difficult. Now I have here an example of something which I called for a while the perfect blue. This is a Berlin blue which was created by alchemical accident. So an alchemist wanted to produce gold, I believe, and instead he got the first pigment that's not natural. We could discuss how blue is it really. And I brought you here a color circle that attempted to sort out the most important 6 basic colors. So you have down there a green, then this yellow again I think is a bit too greenish now. We could agree it's not yellow enough on this projection. Here on this computer screen already it's much better. The red is here a little too dark, and then comes the cyan and the dark blue. And on top of it is a color which in German we like calling purpur, but the English translation wouldn't be purple, I think, but one should call it maybe magenta. And that is a mysterious color because in Newton's spectrum it doesn't occur. And when he bent his color wheel, he was quite at a loss about what to do with this. And to this I come now in the 5th meditation. So when you come up with such color circle like this, you will want to know how many colors do we need to postulate. How many colors are really there and how many of them are maybe only a mixture. So we have always this tendency when we speak about metaphysics, we want the number of items as little as possible. We don't want an abundance of chaos. So if we have 3 million different shades of color that we can distinguish, the question is, can we reduce it on a small amount of colors, which would then be the basic colors, the really importantly existing colors. And in Renaissance painting, the painters came up with 3 colors. And the idea was, it's a bit similar to when we speak about, are there really tables? Well, physics tells us there's no such objects as tables. The tables, they are consisting of electrons, protons, and neutrons, and they are complicatedly arranged into the shape of a table. So the real stuff is these 3 things. And tables exist only in a derivative sense. And now, when it comes to painting, the Renaissance painters came up with a similar idea. Instead of painting the abundance of colors which attack us as we go along in the world, they tried to find pigments such that they need very little of them in order to mix everything else from it. And they came up with the idea that there's only 3 primary colors, and they are here the uppest color, the magenta, then the yellow, and the cyan. With these 3 colors, you can mix more or less all the colors that exist when you have paints. So you need pigments, and you can mix brown, you can mix black even from this, and you can mix red, dark blue, and green also from these pigments. Now, Newton, when he was fighting to get his optics pushed through, it wasn't accepted from the start. So he came up with the first publication in 1672, and the people didn't believe him a word that he detected the primary colors in the rainbow spectrum colors. And the people were not wanting to believe it because Newton suddenly said, well, the white light consists of infinitely many different colors in this rainbow spectrum, infinitely many. This was too much for quite many people who wanted to reduce entities. And then Newton was a bit in a bad situation. He needed support, and as he knew that the Renaissance painters had been reduced the abundance of colors on 3, he also tried to come up with 3 primary colors. So when you read his books, and the question is how many colors are in the spectrum, some of his statements say there's infinitely many, and in fact that's the official doctrine which we believe now. But quite often he said it's 7 colors due to this music analogy, which is a very bizarre analogy. Sometimes he says 5 colors, and then he quite often, when he wants to join forces with the artists, he says it's 3 colors. And these 3 colors we know from our computer screens. So when you mix light rather than pigments, you must obey other mixing rules. This was not known to Newton's time enough. But you can say with Newton, there is no real brown, there is no real white, there is no real magenta. All these can be mixed up from 3 primary colors from the spectrum. And these 3 colors are not the three which you need for pigment mixing, which was magenta, yellow, and cyan, but for the mixing of light rays, in order to make up all the colors on your screens, you need red, blue, and green. And that is the so-called additional, now how does one say, additive mixing of colors. Now, that could bring us to the idea that there is really no brown, and there is really no white, and there's really no magenta. Particularly with the magenta, I think, there is some point which we need to discuss now, because magenta is an important color, and it is all the time downgraded by physicists. And when we speak about the metaphysics of color, I want to now propose that magenta is in much better shape than the physicists would like to have it. Here you have the substructive color mixing as we know it from painting. And here we have Newton's first experiment, which you showed us already in the first presentation. The light ray is split by the prism and gives us the rainbow colors. Here is a photograph of such a spectrum, and you see that the spectrum ends on top of it with a very dark blue, which goes away into black, quite beautiful. The black is not considered part of the spectrum, it doesn't exist. And down there you have a beautiful red, like in a ruby. Is it called ruby or ruby? I don't know. Ruby, thanks. And it also disappears into black, but there's no magenta here. And the Newtonian idea about the magenta is that the magenta is a mixture of many colors of the spectrum minus the green. So if you mix all the colors of Newton's spectrum, you get white. So white doesn't exist by itself, it's only a composition. If you take out the green elements from the white, you get the complementary color of the green, and that is the magenta. So magenta isn't out there in the world, magenta is made up by the human mind. And now I want to reopen the case of magenta, and I want to do it with the help of Goethe and a little help from contemporary quantum mechanics. This is a bit speculative, which I offer to you now. The 5 pessimist meditations are over, now comes the good news. And when we agree on that magenta exists only in this derivative sense, as it's made up by the human mind, mixing, let me say, on the retina, all these photons arrive, minus the green ones, and then our organism creates the impression of magenta, then we might want to see what Newton did to this magenta. So I came up now with a different version of the color wheel than you showed us. So Newton took a spectrum. It depends a little on the material of the prism, and I have assumed a water prism because with water we can best replicate the experiments nowadays, as we don't know quite what the Newtonian glass was made from, so let's do it with water. Newton used water also, so we can make the spectrum. And in some sense, artificially, he made proportions in the spectrum on the space of his screen. And he did it according to musical harmonies. But I must correct the presentation before, because he doesn't do it with C major, and he doesn't do it with the minor harmonies. But when you look at the piano, he does it with an old church harmony system, which is Doric, I think it's called maybe. When you go on the piano from the D to the D, the half tones are somewhat different than when you go in major. And that's how he did it. I would love to know, maybe somebody knows in the audience, why he didn't choose major or minor. Because in Newton's times, these two modes of making musical harmonies was already quite established, while the church tone systems of harmony were already sounding old-fashioned. So it would be interesting what kind of music was Newton listening to, why did he come up with that? But quite artificially, he divides it like that, and then he rolls this color wheel on it. And here, between the blue and the red, you have the D, where it comes back to the beginning. You are up for an octave then. And that's there where the purple or the magenta color is supposed to be. But in Newtonian optics, it's just not there. It doesn't exist in reality, according to Newton. Now, Goethe was famous as a poet, and he was famous as a lover, but I'm not quite sure how much it is known outside the German-speaking world that he spent most of his time doing scientific experiments. and most of the time he did in attacking Newton's optics. Everybody tells us in high school in Germany that this was a mistaken and completely misguided attempt. And that was also how I started when I went into color research. And then when I got into the details of his attacks on Newton, I saw they described an experiment which in official high school physics does not occur. It's put under the carpet. And this is a version of Newton's original experiment. In Newton's original experiment, you have the dark chamber, you have the sun shining, you have a little aperture, and behind the aperture there's a prism. And the prism is lit only on a tiny, tiny fraction of its surface in a round circle that the aperture lets the light through. So you have a prism lit in a very precise dot, and the rest is unlit. Goethe now, the anarchist, decided to turn the tables and switch the roles in this experiment of darkness and light. So instead of having the prism lit in a very, very tiny area, he decided to open the window screen and put the prism into the full light of the day. And then he glued a tiny little wooden circle on that prism. And the diameter was the same as the round hole in Newton's aperture, which he had cut into the window shutters. So everything is the same in this experiment, only the light conditions on the prism is opposite. And what's super interesting, and before I saw it for the first time, I didn't believe it myself, that you also get a spectrum. You get a spectrum. And the spectrum is equally big as Newton's, it's equally beautiful, it's equally differentiated, but it's with entirely different colors. And namely, in the middle you have this magenta, which is missing in Newton's spectrum. And on top of Newton's spectrum you have the blue, and here instead you have the yellow. So it's the other way around, because in Newton's spectrum down there you have the yellow and red, and here the yellow and red is up. Now, when you look at this spectrum without a biased mind, you would like to say, I believe, that this spectrum has equal rights to metaphysical existence as has the Newtonian spectrum. So to the human eye they look equal. And it has been just a coincidence that Newton found his spectrum first, not the other one. If he had been not interested in astronomy, where you look at little white spots at the dark sky, but if he had been interested in biology and had looked through a microscope on little lice instead of stars, the lice are black and the biologists lit the surroundings white, then he would have come up with a spectrum first thing. And his attempt of improving microscope would have led him to take this as a basic thing and not the other one. So it's an historical coincidence with which experiment optics started. Now Newton, of course, has an enormous amount of experiments, and not only this one. For example, he can join the colors from his spectrum back to white. And it's interesting that Goethe claimed that all the experiments that Newton did in his dark chamber can be repeated in the bright chamber, and everything gets the other way around. So when you take these colors and you reunify them, you will get back a black spot, interestingly. And so all the Newtonian experiments have a counterpart where the roles are switched. And that brought Goethe to the wildly anarchistic idea of claiming, just for the sake of the fun, that maybe not white light exists and consists of the different colors of the rainbow, but perhaps it's the other way around. Perhaps darkness exists and whiteness is nothing, as we now believe the other way around, and black would consist of these colors. Now, of course, this is totally crazy from a contemporary point of view, because we now have gotten hold of the photons, and the photons, there are no purple photons, there are no magenta photons, and that should put an end to this crazy idea. That was my conclusion ages ago about this, till I started more and more speaking with physicists. And suddenly I met two physicists who independently of one another developed a very nice idea, which is the end of my presentation now, which is this. The wavelength of photons isn't completely sharp. So because of quantum mechanics, it's a little blurred. There's a superposition of a few wavelengths in each photon. And the sharpness of the interval of which these photons are superimposed depends upon the time which it took to create these photons. So the photons typically are coming into being, I believe, in something like 10 to the power of -7 seconds or something like that. That's an ordinary way of making a photon. And if you take so much time, then of course the time is blurred, but the wavelength is quite precise. Now, if instead you shorten down the time in which you produce the photons on, for example, 10 to the power of -17 or -18 seconds, which doesn't happen in nature often, but in our laboratories we are now able to do it, then, according to uncertainty principle by Heisenberg, the wavelengths which are mixed up in this photon are all the wavelengths from 400 to 800 nanometers. So it would be a white photon until you force it to I don't know, to break the wave function or whatever is the proper pronunciation here. Now, if you have a white photon, it's already interesting. You can make one particle which is white. Newton claimed that doesn't exist, and now modern physics tells us we could make them. They weren't made yet, but we could make them. And now these two physicists said, because I wanted a magenta purple photon, right? The physicists said, well, what we do is we send the white photon through a green filter, and then we force it to be in magenta's color. Now, I'm recently collecting money to get the thing done. I didn't do it yet. The physicists keep saying it would be easy to produce those photons, but it would be not that easy to prove that they have the wanted properties, one by one. So suppose you make many purple photons and you make them hit on a screen. It is supposed to look magenta, but you need quite many of them to create that impression. And the question now is, how can we prove that they were not many different photons hitting the screen on that spot? How can we prove that they were all the magenta ones? And this will be difficult. Maybe in 5 years you check out my homepage and then we might have done it, or maybe it's done already. Okay, thanks for your attention.
Thank you very much, Olaf, and thank you very much also for this exemplary timekeeping. Let me open questions.
So quite a lot of things you're discussing are really to do with the physiology of the eye. So the fact that we have 3 receptors, red, green and blue, I mean, you're showing us colours here, but actually it's all red, green and blue, that's all there is. So the magenta, for example, there aren't, your example is amusing of how you can make them physically, but the real point is you can stimulate both the red and blue receptors in the eye. Even though you don't have photons that do that, you can have a mixture which does it, and that's magenta. So people may not have understood the physiology, but that is a lot of what's going on, and actually a lot of psychology as well. So when I was a child, we had an orange car, but under sodium streetlights it looked white because there was no contrast to anything. So a lot of it is to do with our physiology.
Yeah, right, there's a lot in physiology, but let me tell you, when we started this research to turn the tables and for the sake of the fun to say maybe black consists of all these colors, then the first step is of course to repeat all the experiments that Newton did and then what Fraunhofer did and so on, and always try to invert them. And at the end of the road we would start discussing if with this different alternative complementary physics we might come up with a different theory of the human receptors in the eye. So, of course, the way we describe these receptors now depends upon Newtonianism. So, we analyze and measure them on the ground of the theory of Newton and his followers. And this anarchistic end of my presentation was meant to make us reflect if there couldn't be an entirely different way of doing these things. And then, of course, the case of the receptors have to be reopened.
1, 2.
So I think there's a sort of common thread between this and the so I'm going to really stir things up in a moment. There's a common thread between both this and the previous talk, which is that you're both starting with a spectrum. You've come up with a different spectrum to the previous spectrum. But isn't that actually isn't that suggest that the limit is because that's the starting point? So if I ask, I like the idea of your white photons. If I say, well, what's the colour of a rainbow? I would argue that you guys have all got it wrong, because the rainbow is clearly white. If you go and you look up in the sky, you will see a big white blob, and around the corner of the blob, sorry, not a corner, around the edge of the blob, there's a little coloured bit. And everybody goes, oh, pretty colours. But the colours are just the little chromatic aberration at the edge of the blob. So is it that we've somehow got focused is a good word, isn't it? We somehow looked at the spectrum and at this little blob, and that's kind of derailed, but that's kind of warped the whole way that we look at this, that we're focused. So the rainbow isn't a prism.
Yeah.
The colours in the rainbow aren't the same colours that you get in a prism, because the ones in a prism should be down to an exact wavelength. The ones you get in the sky are an overlap of the various bits of white. Sorry, I thought it was. Sorry, I thought I was using the microphone. Oh, sorry about that.
Okay.
So the colours in the rainbow aren't the colours in the prism, because...
Yeah. Okay, so I was interested in this exchange we had after the first session about measuring the rainbow colors, and I must say that from my observation of the colors of the rainbows, since I do the work with the spectra and with the prisms, I see that each rainbow is different, and I would like to get it more controlled. But I wanted to maybe reply to your question by way of pointing out that I got fierce attacks by physicists on our project from a German guy in Hanover, for example. The name is Zawisza. And he challenged us and said, there's two things that you will not be able to turn the other way around. One is the rainbow, and the other one is the Fraunhofer lines. So I asked him to publish this prediction because I want to repudiate him, and will take some. And it is now published last year, his attack on this. And then I went to my physicist friends who helped me because I can't do the experiments myself. And to my surprise, they said, look, Olaf, with the Fraunhofer lines is easy. We will do that. Give us the money and we'll do it for you. The rainbow will be costly. And I asked how much money they need to turn the rainbow the other way around. That's not trivial, it seems, and they want something like 300,000 euro for that. And I'm busily now applying for the grant to do it, but let us say, at the moment at which we can turn the rainbow, your worry should be addressed, I believe. So it is true that the rainbow colors are not identical to the spectral colors of the prism, but there is some similar relationship between them. The rainbow is more complicated, and the spectrum done by prisms is easier to understand. So I shouldn't have maybe mentioned the rainbow because it was misleading into chaotic territory.
Maybe could I just add to that? I mean, because I think that one of the points about this that you mentioned is also actually colour space, if we're thinking about it, is the three-dimensional space. So you've got red between 0 and 1, green between 0 and 1, and blue between 0 and 1. There are different ways of putting coordinates on this colour space. So red, green, and blue is one of them. But what I try to do in my picture is say, if you look down the diagonal axis, you see the colour wheel is the angle. So it's the angle around that direction. So it's a bit like you're saying, well, you can't say that you're sort of north, south, east, west, very close to the North Pole. If you're at the North Pole, you don't have to walk very far between being due east and due west of the North Pole, because you're in the region of the space where all of the angles are very close together. So what it means in a physical term is, and I think is what you're saying, the colours are all very desaturated, but the hues, the red, green, blue, they're still there, they're just there, they're a lot less strong than they are in the Newtonian spectrum.
Yeah.
Then this is the question that Tom asked me, whether this is actually really the case, and obviously one has to really measure the rainbows and see what is the saturation of the colours in.
Right. May I just make a short remark to this? When you look at the Newtonian color wheel, it doesn't go all the way as we see, right? Sorry, here is the attempt made to give all the colors from human perception. And interestingly, the top color is not present in the Newtonian spectrum. So it's just missing there. And I wanted to defend it and say that if metaphysicians say it doesn't exist really, I bring you experiments where I show you it does exist, so don't worry about purple.
There's a question over here. Could you pass on the microphone?
You said towards the end of your presentation that you wanted to look at it the other way round to see might be discovered, inverted commas. This strikes me a little bit like the old problem with phlogiston and oxygen, and they eventually got it the right way round. Do you really think you might get an added insight by what you're doing? That's one point. The other one is, what's happening now with the experiment that Alain Aspect used to be doing? I know this was with the two-slit experiment, but it was to do with the, whether it's one or it's several wave packages, should we call them, because you got onto that wave package idea towards the end of your presentation. Yeah. So that surely relates to what you're talking about. And the other one was, it strikes me, this idea of whether you see something, whether it really is or it isn't. This is the early part of your presentation. It's a bit like the old problem of quantum mechanics, and whether you, let's say the Copenhagen interpretation, you only see it when you're looking at it, or it's only in existence when you're looking at it. Can you comment on these things, please?
Yeah.
Three things.
First, as to this last question, I would like to say metaphysicians cannot bring knockdown arguments that one way of looking at these things is better than the other one. And it is a matter of human practice, I would say. If we come back to this naive realism where you just say everything is out there the way we see it, which is humanistic, or if we detach ourselves from our organisms so much that we trust only the equations done by physicists. But that's a big issue in metaphysics, and there's no arguments. It's just a matter, I would say, a matter of style of thinking. It's a matter of taste, of character, which option you choose here. And I'm glad now with the Goethe-Putnam solution, and but that's my personal makeup, I would say. And now the other issue, I just addressed the one thing about the Thomas Young and the double-slit experiment, where we were convinced that light can be described as consisting of waves. And when you do a grating, no, is it called grating or grate? I don't know. Grating, yeah? Okay, a grating, and you send the light through, you get these spectral colors, you have some maximum in the middle, and then you have these other rainbow colors, and this looks very Newtonian and can be used in order to calculate the wavelengths of the different colors. So the simple geometry, you see where does the blue land, you know the distance of the stripes in this grating, and then you calculate it. And my opponents with this other theory, this fun theory, my opponents said, well, you cannot assign wavelengths to the dark rays which come from the Goethe spectrum. And so I asked my friends from physics if they could repeat that experiment the other way around. It can be done. So we can send a shade through a grating surrounded by light, and you get the exact color opposite of the original experiment. And then we can assign the wavelength of 600 nanometers to, for example, the magenta rays. And this craziness can be repeated can be prolonged for a long, long time. And I have not yet seen the moment where the symmetry between these two systems breaks down. Now let me say two things about why it was claimed by Goethe. Goethe did not claim that darkness is everything and white is nothing, so he didn't turn the tables around. He used it only to convince us that Newton's logic is flawed, because with the same logic Newton came up, he can claim with his experiments this opposing theory, and he said both are inadequate. What we should do, we should accept the true existence, metaphysical existence of both factors, darkness and light. They were making up the world of optics before Newton showed up. Newton was the one who pushed us into the dark chamber, claiming that in the dark chamber there's no optical effects minus this little light which goes through. But that was there was no reason for it. It was just Newton's style of doing these experiments, and doing them the other way around was neglected in the further path of history. Now, as I'm in Great Britain, I would like to add that in the beginning of 19th century, there actually was a scientist who claimed that Newton had got it all wrong, and that white is nothing, and that the darkness is the power of optics. And this guy, I don't know how much he is known, the name is Thomas Reid from Edinburgh. He was an eyes doctor and also president of the Physical Society of Edinburgh at the beginning of 19th century. He published one book. He promised 2 more, but they didn't appear, I think, and he published 6 to 7 essays about it. And he took it totally seriously, this theory, while Goethe did it only in order to attack Newton.
Thank you. One final question at the back, and then I'm afraid we'll have to close questions for this session. If you could keep the answer compact, please.
Thank you. That was utterly fascinating. Yeah, one slide just whipped past too fast for me to read the bottom. You mentioned Schopenhauer. What was his comment?
Right.
Please, thank you.
Yeah.
Cheers.
Okay, I forgot him. Sorry. So he was the guy who said that in all cultures there's just these 6 colors. So he had an early version of this basic color term theory of Berlin and Kay, but he said it's just 6, and he studied Greek language, Latin, and many other languages, and he claimed that there's an ideal color always, and then he connected it in an interesting manner to Platonism, saying that it is just these 6 colors, metaphysically, and really we never encounter them because our life here is too dirty and there's no perfection here. And even if you look into something that looks most perfect yellow, it's never the Platonic perfect yellow. We can only imagine this Platonic yellow, the ideal yellow. And one of the reasons why he was right, I think, about that, why one might go back really to this Platonism here is that if you ask an artist to paint you a perfectly yellow painting, or if you make it on your computer screen, and you stare on it for a while, the impression that you see is not stable because your human eye wants to get the opposite color. It busily works against this yellow, so it's never a stable impression. It is always vivid, and only if we had the very Platonic idea of the true yellow, it would be stable. Platonists wanted to have a stability in the objects and not this floating chaos in our dirty world down here. This is a metaphysical thought which I gave on the screen in order to please Joanna because she wanted some metaphysics.
Well, thank you very much, Olaf, for this journey into the metaphysics of color. I think it's set up